So we're going to use Euler's method and 6 equal subdivisions to estimate the value of x when x equals 2 if the initial point is negative 1, 1. First thing we need to do is to figure out what our delta x is here. In this case, we're not able to choose it arbitrarily. We're told that we're supposed to use 6 equal subdivisions. And we're going to be going from x equals negative 1 to x equals 2. So we're going to basically use the b minus a over n approach that we used when we were integrating, when we did the Riemann sums. So here we're going to use the final x value, which is our b value, our 2, minus our initial choice of x, which is negative 1, over the 6 equal subdivisions we need to have. So here we end up with 2 plus 1, which is 3, over 6, which happens to be 0.5 here. Okay, well that allows us now to put our table together. Our first column has x comma y, and our initial point was negative 1, 1. Let's go ahead and put our next series of x coordinates in. So we've got negative 1 plus 0.5, which would be negative 0.5 comma something. Negative 0.5 plus 0.5 is 0. 0 plus 0.5 is 0.5. 0.5 plus 0.5 is 1. 1.5 and 2. Let's see, that's going from the first one to the second. It's one subdivision. 1, 2, 3, 4, 5, 6. There's going to be 7 rows, but 6 subdivisions, and they're all equal distances, equal spacing for x. So this differential equation is over here. It's x plus y. This is one we do not know how to solve with separation of variables. We'll be able to solve it pretty early in differential equations, but at this point we do not yet know how to do this. So we're going to be able to come up with some meaningful information from this, though, using Euler's method. So dy dx is our second column. Let me put in the titles of the others. Delta y is dy dx times delta x. This is our tangent line approximation to delta y. It's how far we would go up on the tangent line, up or down, mind you, because we could be going down sometimes if we have a negative rate of change. Then our new y, or y plus change in y, is our last column. Alright, so let's see here. dy dx at negative 1, 1, we have x plus y. Negative 1 plus 1 is 0. Then we have 0 times 0.5, our delta x, which gives us a delta y of 0. Negative or positive 1 plus 0 is still 1. Alright, we're not going to draw it this time. I'll show you on the Excel demonstration in a few minutes what this looks like. We put the 1 down here. That's our y value. We take that now and add it to the x. So negative 0.5 plus 1 is positive 0.5. 0.5, our dy dx, times 0.5, our delta x, which was right up here, gives us 0.25 for our approximation of delta y. We add that to the 1 we already had to get 1.25. We put it down here, 1.25. We add it to the 0, we get 1.25. We multiply 1.25 by delta x, 0.5. That gives us 0.625. Adding that to 1.25 gives us 1.875. So we get 1.875 here. Adding it to 0.5, we get 2.375. Multiplying that by 0.5, I won't write it this time because it's getting longer, we get 1.1875. Adding that to 1.875, notice they are a little different, we get 3.0625. That will come down here. Adding it to 1, this is easy enough, 4.0625. Multiplying that by 0.5, we get 2.03125. Note that when you do some of the examples, you'll have to round at some point, keep 5 decimal places. Here we didn't have to do any rounding, so we're just keeping it as it is. Adding this value to the old y value gives us 5.09375. That's our new y value at 1.5. Adding 1.5 to that to get our slope there, it's 6.59375. 5 decimal places without rounding here, just had that many in this particular case. Divide that by 2, we get 3.29688. I think I may have rounded there to make that happen. Okay, then adding that to 5.09375 gives us 8.39063. So we get 2, 8.39063. And now we can answer the question, when x equals 2, y will be approximately 8.39063. So this is the answer to the question that we came up with using the Euler's method chart or table. Alright, let's go ahead and enter this into the Excel worksheet and see if we can't just double check that this works. So let me see here. First I'm going to choose a different one, and I think x plus y is in there already, which is helpful. We're going to start with a different point here. So let's see. I need to enter a -1. We'll delete what's there. Put -1, and it's got to be 1 on the right of that. So press enter there. This one needs to be a 1. So put 1 in there. Okay, and the first slope was 0. Sure enough, that matches. And let's see, we had 0.5 up here, so I suppose we should put in that as well. So 0.5, and let's go ahead and try it out. So next step, and so on. Maybe you put some of the points in there so we can see them. And I think, did I just pass 2? Oh, I went past 2, but you can see here what we got, 8.39063. We see the value matches what we came up with in our table anyway, and we see what the slopes are. Didn't need to finish that line off, by the way. I'm going to reset it, show you real quickly again. Alright, that's where we'd end when we do the table, and so this is exactly what we get here in this Excel worksheet. And notice the picture, which gives us some satisfaction as well, seeing how this looks like it should, go in the right direction along this slope field. Now again, if we want to improve on this, we could try to use a smaller value of delta x. So I could backspace, maybe put in 0.01, and if we do that, let's see, press enter, and we're going to take those dots out. It's going to get pretty crazy. And if we hit Euler's method up here, it'll ask us the number of steps. Let's see, I'm going to put in, well, we needed 6 to go with 0.5. How many do we need to do this? Well, it's going to have to be quite a few, right? Going over 3 units. So 300, I think, is what we might need. So 300, enter. And let's just go ahead and take a look at what we came up with here. So 16.7885 is what we have at 2, and that's quite a bit farther up than the 8.39063 we had, but we could have guessed that we weren't quite on. This is going to be much closer to the actual curve. The picture doesn't look terribly different, I suppose, but it was going over here somewhere when we did it. So notice how much tighter it goes with the slope segments here this way. To be honest though, if we were drawing this in by hand, we would have done much better. We would have been much closer to the more precise Euler's method here, using a 0.01 delta x than if we use this large delta x, which is way off, as we've seen here. Now of course by hand we're not able to make really impressive results with Euler's method, but as you can see, the computer using a very small delta x can get a much more impressive result with this technique. And like I said before, there are variations of Euler's method that do even better, to do quite a bit better than this Euler's method does at approximating the curves that are solutions to a differential equation. So the reason for covering this is to be able to deal with differential equations we cannot solve either now or later. This is one we'll be able to solve later, but we can't solve using separation of variables. Okay, I hope this has been clear. This particular Excel worksheet is not necessarily available yet, but you can certainly use your calculator. There's an Euler's method there that you can use to verify your answers. I just want to be sure that you really do know how to fill in the tables using the information in the table to find an Euler's method, the results of Euler's method here. So we might cover that in another video, how to use the calculator program.